All right. Again, welcome everyone. Our numbers keep trickling in. As you join, feel free to put in the chat what part of the country you're joining us from, or again, what summer blockbuster movie you're looking forward to. And again, welcome. So with that, hello everyone. Thank you for joining the EPA's WaterSense program to talk about really that untapped potential. We're going to be looking at an assessment of municipal and industrial water efficiency opportunities in the United States. My name is Kersey with the EPA's WaterSense program. As always, you are encouraged to please type questions, suggestions, your own experiences in the chat. We're going to have plenty of time at the end for a Q&A. Also, if it turns out that there's a lot of audience questions, Bruk and I are happy to stay past the hour for any folks that want to stick around. The phone number is posted above if you're having some computer audio issues, but hopefully not. And we are recording right now, and we'll be sending out the slides afterwards. In case this is your first time joining us, our WaterSense Wednesday webinars are aimed at really encouraging commercial, industrial, and institutional CII facilities to adopt water efficiency and water management strategies. I say this at every webinar. If you'd like to go from being an audience member to being a speaker, please let us know. Let's keep sharing our water conservation efforts, programs, and achievements just to help each other out, to make progress, and to connect. We really do get a lot of follow-up emails after each webinar, and it's a positive testament to the information sharing that happens afterwards. Now I'd like to introduce our speaker for today. Dr. Bruk Berhanu is a senior research specialist at the Pacific Institute, where he works on research projects related to water conservation, efficiency, and reuse. Bruk previously worked in the municipal water, wastewater utility industry, supporting infrastructure planning, demand forecasting, and water reuse projects at multiple spatial scales. Bruk received his PhD in civil engineering from the University of Texas at Austin. Bruk, I believe that's Longhorns, right? And is a registered professional engineer in Oregon. His doctoral research focused on the feasibility of integration of on-site reuse strategies into water, wastewater utility planning, and management. In case we've got any new viewers, WaterSense is a voluntary label and partnership program that was established by the US EPA in 2006. We have a wide variety of residential and commercial products that are eligible for the WaterSense label that can be used in residential and in CII facilities. So far, there's over 45,000 product models that have earned the WaterSense label in the 9 different categories that you see here. Reach out to us or just check out the website for more info. I'd also like to make a plug. Please check out WaterSense at Work. These are our best management practice guidelines. We cover several aspects of the CII space, such as mechanical systems, irrigation, commercial kitchens, plumbing fixtures, among many others. It really helps to get folks started if you're starting from square zero, square one. And lastly, if you're interested in becoming a WaterSense partner, we encourage you to please apply. It's free, and we'd love to have you on board. And so with that, Bruk, let's go ahead and have you steal the screen from me.
All right, sounds good. Let me know when you can see the splash screen.
I see it.
Perfect. Well, I'll go ahead and get started then. Yeah, good morning or good afternoon, everyone, depending on where you are. And thanks for joining for this webinar. My name is Bruk Berhanu, as Kersey mentioned, and I'm a senior research specialist with the Pacific Institute. I'm going to be talking a bit today on a report that we released at the end of last year, looking to quantify the volumetric potential for municipal and industrial water efficiency at the national scale throughout the United States. For this presentation, I'll focus a bit in more detail on the CII sector. So just some quick background. As I mentioned, I'm with the Pacific Institute. We're a global nonprofit think tank conducting water resources related research, combine evidence-based research and analysis with outreach and engagement. Our goal is to catalyze the transformation to water resilience in the face of climate change. This work is the second in a three-part series of national assessments looking to quantify the potential for different alternative water supplies. We started with stormwater capture in the US and released that report at the beginning of 2024. In the fall of last year, we released the report that I'll be talking about today, which is the Municipal and Industrial Water Efficiency Assessment. And then later on this year, it says spring, it should say probably in the fall of 2026, we'll be releasing our third assessment looking at municipal and industrial wastewater reuse. I'm speaking to y'all today as the project lead for this assessment, but I, of course, did not do this work alone. I was supported by a great team at the Pacific Institute of the faces and names that you see on the slide here. And this work was also supported by an illustrious expert advisory panel consisting of folks from across different sectors, academia, the utility space, private industry, government, other nonprofits, and their names are all listed here. They really helped shape not only the scope of the analysis, but then also were instrumental in outreach and engagement, and continue to be instrumental in outreach and engagement, as evidenced by this webinar. So for today, I'll give a little bit of background just on water efficiency and kind of what we looked at as part of this assessment, and then I'll talk through some of the analytical approach that we use to estimate what we're calling the volumetric potential, or how much water is there available to save from increasing municipal and industrial water efficiency. I'll highlight some key findings, as I mentioned, focusing a bit on the CII sector, as well as some recommendations that can be found in the report. There was way more in the report than what I'll be talking about today, so I highly encourage y'all to read it. You can find it on our website if any of this is of interest to you. And as Kersey mentioned, I'll be available for Q&A, and I can stay on a little bit after the webinar ends as well. So just for some background, so we've seen really what we call this phenomenon of decoupling between water use and growth occurring in communities all across the US over time. And what we mean by decoupling is that as population continues to grow, total water use actually, in some cases, doesn't increase as quickly. In other cases, it actually remains relatively flat. And in some places, it's even declined. You can kind of see two examples of that in these two charts with Los Angeles on the left and Denver on the right. Los Angeles has shown pretty strong, consistent population growth over the past several decades, whereas its overall water use has remained relatively stable or consistent with some, year-to-year fluctuations. And then over in Denver, we actually see water use similarly staying pretty stable in that blue line, while population has increased dramatically, as shown in the green line. And this is really a trend that we've seen even when you look at the national scale. This chart shows the total water use for just the municipal and industrial sectors across the entire US as estimated by the USGS. They release their estimates of water use every 5 years. And the solid blue line shows kind of the total overall water withdrawals in million of acre feet per year, whereas the dashed line shows per capita water use. And the gray bars kind of show population. And so the story really is being seen not only in individual communities, but at the nation scale, where water use has remained relatively flat or stable, whereas per capita water use is continuing to decrease and population continues to increase. And so a big portion of this is driven by improvements in water efficiency over the past several decades, both in terms of technology as well as in terms of behavioral patterns. And when I talk about water efficiency, I'm really talking about technologies and practices that allow us to use less water for the same level of service. So there's nothing being sacrificed in terms of what you're using the water for. There's only just a more efficient rate of water use for that. A more efficient rate of performance for that water use. And these images just kind of show a few different examples, landscapes, more water-wise landscapes being one of the clear examples, as well as high efficiency fixtures and appliances, and even getting better at managing utility side leakage or water loss. And so while these strategies are great for helping us reduce our overall water use, they also provide a host of other benefits. This image or this slide kind of shows kind of a few different dimensions of what we call co-benefits or multiple benefits to water efficiency beyond water savings. Of course, they help reduce vulnerability to water shortages and improve water supply resilience, but they can also be used for environmental benefits and improving water quality. And at the same time, they support customer affordability by reducing your water bill and in some cases your energy bill by reducing your hot water use, for example. But we often hear, accounts from individual communities or from other folks that say that water efficiency has really reached its limit, and there's really not much to save, or all of the low-hanging fruit has already been picked. And so what we wanted to do was ask that question of, how much further can water efficiency take us in terms of reducing our water use? What is the kind of total remaining volumetric potential today from strategies and technologies that are currently available to further reduce our water use through efficiency. And so we wanted to look at those opportunities across sectors, across the residential sector, the CII sector, and as well as for utility side water losses. And the estimates that I'll talk about kind of reflect a current day snapshot. In this assessment, we haven't looked at potential impacts for future population growth or development patterns, but that's something we hope to do in future work. And so now I'll talk a little bit just about kind of the analysis approach that we used to answer this research question. As I mentioned, we looked at kind of three different sectors of water the three primary sectors of municipal and industrial water use. That's water use in the residential sector, in the CII, the commercial, industrial, and institutional sector, and for utility water losses. And those are kind of shown in the light blue squares kind of in the middle of the slide. To the left of those, we also looked at water use not only at the sector level, but also try to disaggregate what that water use and what those water efficiency savings opportunities are at more granular levels than just the sector. So for residential, we looked at both indoor and outdoor water use, and we even were able to further break out indoor water use into individual end uses or fixtures and appliances that are typical amongst homes and apartments. For the CII sector, as I'll get into, the CII sector is very diverse, both in terms of the types of water use as well as the end uses apparent, and there really just isn't data to be able to do that granular analysis at this moment. But we were able to provide estimates that are disaggregate kind of the CII sector into what we call major subsectors of water use, and those are kind of major industries, and we'll talk a little bit about those in more detail. And then for utility water losses, we really just focused on what's called the real losses, or the physical volume of water that leaves water distribution systems through things like leaks, main breaks, unauthorized use, etc. There's a whole other side to water loss called apparent losses, which are really more related to how we measure how much water is going into and out of the water distribution system, how much is going through customer meters, and there's of course always going to be a small amount of error associated with any kind of measurement. But for our purposes for this assessment, we did not look at those apparent losses. So the first step to answer the question of how much water can be saved is to get an estimate of how much water use is currently occurring. I mentioned the USGS water use estimates that are released every 5 years. Those are typically done kind of at major sector levels, thinking like the agricultural sector, or the mining sector, or the electric power generation sector, and then municipal as well. But since we wanted to get a bit more granular into that municipal and industrial kind of sector, we looked at a variety of data sources to be able to kind of help us estimate help us get a more granular estimate of current day kind of municipal and industrial water use. The primary data set that we relied on was a set of monthly utility billing records that were broken out by residential, commercial, and then total water use for about 100 utilities across the country. And those utility locations are shown in these gold diamonds in the map on the left here. That data set was compiled by a group of researchers from Colorado State University who did the painstaking work of surveying and calling and collecting data for each of those utilities. And that data set represents monthly water use by sector from anywhere from 2005 to year 2017. We also relied on, or we also were able to work with the company Flume, that is a kind of home water use monitoring company. They sell and install devices that allow homeowners to monitor their water use in real time and actually can disaggregate their water use not only by indoor and outdoor water uses, but also by the specific fixture that's using water. And they have kind of a set of analysis algorithms that they use to be able to identify, when water flows through your meter, what is it being used for? And so that allowed us to get this more granular look at how much water is being used, not only at the residential sector as a whole, but also across residential end uses, both indoors and outdoors. And we purchased a data set from them consisting of summary statistics of water use rates by end use for about 20 different metropolitan statistical areas. And those are shown in the map on the right, with the color indicating the number of devices that were installed in each of those MSAs. And so you can see there's pretty good coverage of the country, both in terms of our billing data set in the map on the left, as well as the Flume end use data set in the map on the right, with some gaps that we were able to fill in. We also used a bunch of different other relevant input data sets to help us complete kind of that water balance picture, population and employment from the Census Bureau, water use intensity metrics from the EPA's Energy Star Portfolio Manager tool, and one of our intrepid researchers spent a good amount of time collecting individual water loss audits from utilities across the U.S. To actually help us develop our baseline estimate of water loss. And I think from those were compiled from where they were available at the state level, and I think our final data set consisted of roughly 2,000 or so utilities. Keep in mind, there's over 40,000 utilities across the country, so it's certainly not an exhaustive data set, but it allowed us to at least take a first step in trying to get our hands around how much water loss is actually happening across the country. I'll talk a little bit in more detail on the CII sector. And so, as I mentioned, the billing data that we had for each of the utilities shown in the gold diamonds were broken out by residential, commercial, et cetera. And so using that commercial data, we combined it with some external data sets, and number of employment or number of employees or employment totals, which is generated by the U.S. Census Bureau and their economic census that's released every 5 years. We used those two, as well as some floor area per employee relationships that we estimated from the Commercial Building Energy Consumption Survey that's administered by the U.S. Energy Information Administration, to develop estimates of square footage by subsector within the CII sector across the country. And then once we had square footage estimates, we were able to estimate water use intensity, which is a metric that's commonly used to benchmark and compare water use data in the CII sector in gallons per square foot. And we were able to compare our baseline estimates of water use intensity to benchmarks that were reported in the Portfolio Manager tool. Oh, and I think this slide is a duplicate, so I'm just going to go ahead and skip over it. And so all of that work was just to get us to a current day kind of baseline estimate of water use across the country. The next step was then to look at different efficiency scenarios, how much water could be saved by taking different actions of increasingly ambitious water efficiency and conservation performance, and then estimating what the savings come from taking those actions, basically as the difference between our current day water use and what water use would be under these scenarios. So we developed 3 different scenarios to look at of increasing efficiency. The first on the left is the basic efficiency scenario, and overall that kind of represents basically meeting minimum existing standards for efficiency and water use. The high efficiency scenario kind of reflects the next step forward. A lot of states and communities are already kind of at this level, but so far, really, the federal standards, for example, really kind of reflect what's in the basic efficiency scenario, and then we have programs such as Water Use and Energy Star that reflect these higher efficiency scenarios. So, for the high efficiency scenario, we kind of looked at average performance or nominal performance of kind of more efficient entities or efficient fixtures and appliances. And then we had our leading edge efficiency scenario, which is really trying to take the best in class performance or technology available and understanding what the water savings could be from 100% adoption of those practices and those technologies. So each of these scenarios represent kind of an optimistic upper level of what can be saved. And of course, the next step is understanding what's likely to happen. That it takes a whole other set of analysis that others have done in different areas, and that's something we hope to be able to do as a next step for this national scale assessment. But first, we wanted to start with what is on the table, what's actually possible, and then try to refine that further. So the first kind of row across the top here represents those scenarios for residential indoor water use. We use federal minimum standards for the basic efficiency scenario, kind of the average fixture and appliance performance from WaterSense and Energy Star labeled devices for the high efficiency scenario, and then the best available performance for the leading edge efficiency scenario. For outdoor water use in the residential sector, our basic efficiency scenario really focuses on just eliminating over irrigation or irrigating in order to meet the evapotranspiration needs of a typical turf landscape. Whereas then the high and the leading edge efficiency scenarios reflect more changes to the composition of the landscape, such that your water use reflects one that is a landscape that is the water use for a landscape with medium water use plants and and moderately efficient irrigation in the high efficiency scenario, or low water use plants and efficient irrigation in the leading edge efficiency scenario. For the analysis, we really just used a performance-based approach that kind of reflects water use that are equivalent to these landscapes. However, we don't really make any prescriptions. We remain agnostic as to how that level of water use is achieved. And so theoretically it could be done by other things like just replacing turf area, reducing turf area, deficit irrigation, just watering less than what your plants need. It doesn't necessarily require, landscape transformation or improving irrigation systems. And then for the CII and water loss sectors, we used a similar kind of performance-based approach. And for the CII sector, it was informed by those water use intensity benchmarks that are available by state and by subsector from the Energy Star portfolio manager tool. And we essentially estimated what the water that could be saved from our current water use to a performance level that meets the bottom 20, the bottom 25th percentile performance, the middle median performance, and then kind of the most efficient 25th percentile performance for similar entities on a state-by-state basis. And so in cases where we've estimated that the baseline water use was already meeting the same standard as one of these efficiency scenarios, we estimate a savings of 0. So we only are really estimating what the potential is in places where they're not currently meeting one of these efficiency scenarios. So now I'll jump into some key findings and talk a little bit about some of the case examples that we talk about in the report. And I'll start with kind of national level results, get a little bit into the individual sectors. There's way more results than what I'm showing here today, so highly encourage you all to read the report and definitely reach out with any questions afterwards. So top line number across the country, we find that the total potential for efficiency would result in reduction in current water use ranging from 25% in the basic efficiency scenario all the way up to 60% in the leading edge efficiency scenario. And so what that means is, getting homes and businesses and communities to meet just existing federal standards and kind of nominal efficiency performance in the CII and water loss sectors would result in 25% water use reduction. And then going beyond that to meeting more aggressive standards and specifications could actually increase the savings potential up to about 60% of current day water use. And just a fun fact, that kind of results in water use that was relatively close to kind of the total water use for the country in the late 60s or early 70s. And as you can see, this graph kind of shows a breakdown of that savings potential kind of broken out by sector. And what we find is that there really is water savings potential in every sector. And then I'll show some maps that also kind of point to water savings potential existing in every state as well. Oh, and I'll just mention that all of these results are presented in millions of acre-feet per year. If you're more used to like millions of gallons per day, for example, it's a relatively easy conversion of there's about 1,000 acre-feet per year per million gallon per day. So you can kind of use that conversion if that's helpful. So what this chart now shows is just a breakdown of just the residential water use savings. And so on the very bottom, we have kind of just the outdoor water use savings potential by efficiency scenario, basic efficiency on the left, leading edge efficiency on the right. And then the different end uses are stacked based on their kind of from the largest potential to the smallest potential, going from bottom to top. So what we find is after accounting for outdoor savings potential, we find that toilets and shower heads have the highest savings potential inside the home, followed by faucets, as well as low flow leaks, and then finally clothes washers and dishwashers at the top. And you have to squint really hard to see the sliver for dishwashers in yellow there. There's just a relatively small savings compared to the other end uses. But hopefully this kind of gives you a sense of the rough proportion of savings opportunities across the different end uses. And a lot of this is driven, especially in the leading edge efficiency scenarios, by continuous improvements to the technologies that are available. There are, residential, the federal standard for toilets, I think, is 1.5 gallons per 1.6 gallons per flush. The WaterSense standard is 1.28 gallons per flush. But there are models available that use 1 gallon per flush, or I think as low as 0.7 gallons per flush. So that continuous improvement in technology is really driving a lot of the savings potential. When we look at the results geographically, this map is showing just for the outdoor potential. We do see a lot of potential in states like California, especially in the leading edge scenario, in the Southwest, Arizona, Texas, for example. But we also see maybe a disproportionate potential in states that aren't traditionally associated with water scarcity and ongoing long-term drought, especially in places like in the Southeast and in the Northeast. But what we're also finding is that these areas, while they might not be experiencing kind of the chronic long-term drought that's more familiar in the Southwest, they are seeing increasingly frequent seasonal and cyclical droughts that are currently straining their water supplies. And so a focus on residential outdoor efficiency and conservation could be a beneficial solution to helping kind of mitigate the impacts of some of that increasingly frequent water stress in those regions. And I forgot to mention, this map is showing kind of the percent reduction, the water savings as a percent reduction from the baseline. So the darker colors indicate a larger potential percent reduction. So now I'm going to switch to the CII sector, because this is a CII, WaterSense CII webinar. And I wanted to talk first a little bit just about the baseline water use in the CII sector. As I mentioned previously, the CII sector is incredibly diverse in terms of how much water is being used within an establishment, even what end uses are present in different establishments. You can think food service establishments will have very different fixtures and end uses beyond the bathroom than, for example, a healthcare facility or an industrial facility. And so when we analyzed the the CII billing data and disaggregated it into sectors, we found results that kind of confirmed that variability or heterogeneity. On average, the food service sector has the highest water use intensity in terms of gallons per square foot. But that's really variable based on which sector you're looking at. That's kind of followed up by offices, then healthcare establishments, accommodations. And that's not to say that those are using the largest volume of water. They just have the highest kind of normalized water use per square foot. But then if you look at the error bars for each of these subsectors, you can see a wide range of variability. And these results kind of show the median or the state level median. So the error bars represent the 95th 5% range across all 50 states. And so it's not only variability or diversity across subsectors, but it's also diversity across the country, and just in terms of how much water is being used. These two maps here show the largest sector in each state, kind of by the both the water use intensity as well as the overall kind of volumetric demand, or the water use volume. On the left, the water use intensity. In every state, food service has the highest water use intensity in terms of gallons per square foot. And that's kind of consistent with the last slide I just showed. But that doesn't always translate into the highest total water volume. I think it's the case for places like Texas and Louisiana, Oklahoma, and Arkansas, but you can see in the western half of the states, different categories outside of kind of the major subsectors actually have the total water use volume, or the highest water use volume. And then you can see a smattering of like healthcare facilities, for example, or offices on the eastern side of the country. I will note that other category is kind of a catch-all for kind of more specialized subsectors that didn't fit into the major subsectors that I showed on this slide here. And so it makes sense that would be the largest kind of quote unquote subsector in a lot of states, but that just means that, you know, none of the major subsectors are really the largest water user. And one thing I'll mention about the industrial sector in particular is that you can think of the industrial sector spanning a pretty wide range of facilities, ranging from manufacturing to data centers to other industrial uses like processing, things like that. And they all have different rates of water use. And so, but they all tend to be kind of large physical footprint facilities. And so even though the water use intensity might be low, their overall that doesn't necessarily mean their overall water use is low, like for an individual establishment. So now we can talk a little bit about the efficiency potential. And so this chart, kind of similar to what was shown for the residential side, shows the water savings for the 3 different efficiency scenarios, kind of broken out by subsector. And then also similar for the residential, it's kind of ranked from the largest savings opportunity subsector on the bottom to the smallest savings opportunity subsector on the top. And so what we see is, you know, as I mentioned, food service has the highest water use intensity across all states. And so we find that there's actually the largest volume of savings potential for food service establishments across the country. Excuse me. That's followed up by offices and then healthcare facilities. And then as you get into other subsectors, it kind of depends on which efficiency scenario we're looking at to determine how much water savings opportunity there is. Finally, I'm sorry. One other thing I wanted to mention on this topic was that due to the kind of data inputs that we used, a lot of these results are going to be clustered by census regions, so kind of groupings of state, because that's where we were able to find summary metrics for. And so one of the things we want to do is try to collect more granular state level data for things like square footage estimates or employee per square footage estimates, because that ends up driving a lot of our results. So now switching to water loss, we find that water loss savings potential is highest in the eastern half of the United States. Now, intuitively, that tends to make sense. Water systems in the eastern half of the United States tend to be a lot older than in the western half of the United States, and so might have infrastructure that's more prone to leaks and breaks, aging infrastructure that hasn't yet been repaired or replaced. And so, just at an intuitive level, that makes sense. But I'll mention that this data set was kind of caveated similarly to the CII data set, where some of the inputs were aggregated up to the census region scale, which is why you kind of see similar savings potential in the Mountain West area, for example. And so one of the things we hope to do in future work is to better disaggregate kind of these some of these inputs to be able to get state level assessments. But what we hope is that this assessment kind of provides a starting point for both us as well as for other researchers to kind of continue this work, refine these estimates further, especially for individual states looking to make changes to improve their water efficiency. So I'll just touch really briefly on a couple of case examples that we talked about, or that we talk about in the report, that kind of also speak kind of qualitatively and discuss more proactive or more innovative approaches to water efficiency and reducing water use that we weren't able to include in our analysis, but wanted to speak to. As from a discussion perspective. Those are kind of taking more proactive approaches to water loss control, looking at certification systems that certify whole home efficiency instead of individual fixtures or appliances, and then as well as looking at something called structural or behavioral waste, that is kind of the water use that's baked into how we design our plumbing systems and kind of how we use water that isn't necessarily tied to a specific technology. So I'll just plug those if you're interested in any of those topics. We do talk about them more and provide more information in the report. So just to kind of summarize what I talked about, we've found that there are water savings opportunities in every sector and in every state. And depending on the level of efficiency that you're going for, those opportunities can reduce kind of baseline water use from anywhere from 14 to 34 million acre feet per year. That's roughly equivalent to a 25% to 60% reduction from baseline water use levels. So we also provide a set of recommendations for policy and practice in the report, kind of based on these results, as well as based on our understanding of water efficiency. They can be grouped into these four major categories: expanding funding and financing opportunities, increasing financial and non-financial incentives, updating codes and standards, and then expanding data collection and monitoring. And just for the sake of time, I might just skip over to a few of the more CII related ones, which are really come in the expanding data collection and reporting side of things. As I mentioned, there's a lot of heterogeneity, a lot of diversity in the CII sector, and there really just isn't great like national scale data that really tracks water use across all of the different types of establishments. CII establishments. And so we do have a recommendation that includes, calling for states and local governments and utilities to start to require more regular reporting of CII water use, using metrics that can allow for comparison, as well as for some of this prospective work to look at water efficiency potential. But before that can happen, there has to be a consistent kind of taxonomy or classification system. Every utility in every state either doesn't have a system for, categorizing the different types of CII customers as they have, or they have a different system than every other state. And so we think that the Energy Star portfolio manager's taxonomy is a good starting point. Of course, there are going to be facilities, as I mentioned, with that other category that don't fall into their classification system. And so, but using that as a jumping off point to develop really just the goal is to have a standardized system that can enable some of that comparison and some of that benchmarking across different states and for the country as a whole. So with that, I think we'll switch to question and answer. I was told that these slides will be made available afterwards, and I have a link as well as my email in the chat. But yeah, looking forward to hearing everyone's questions and having a good discussion.
All right. Well, with that, first off, Brooke, thank you to you and the whole team there at Pacific Institute just for your work and for taking time out of your day to share a bit about it. And again, I want to give a shout out to some of my colleagues. They've been in the chat putting in some useful links. My colleague Grace has been there in the background, just keeping the gears moving. And again, want folks to know that we are working to line up the webinars for the remainder of the year. The upcoming June webinar, we should be sending out the registration real soon, so stay tuned for that. And so, Brooke, I think you've got your work cut out for you. It started as a trickle, now it's a flood, which is good. So I'm gonna just, we've got a few questions in the chat. We have some in the Q&A. Brooke, I'm gonna pitch them to you in the order that we got them. So, the first one that I saw come through was with regards to the flume data,
Mm.
like, did you all normalize or that flume data? Given that flume users, they proactively purchase and install watering monitoring devices, they may not necessarily represent, all water users. I think, for example, for this particular water utility, their flume users tended to use more water than the typical customer. But that customer could also have significantly lower leak rate. So, I don't know, any commentary on the flume data?
Yeah, no, those are all great points. We did look at the flume data and compare it to kind of previous national studies that have kind of end use disaggregated water use data. They were provided to us on a per capita basis, so that we could try to get a sense of um, water use rates. How, what duration do different people shower for? How many times do they turn on their faucet for how long? Um, there's not a lot of evidence that the indoor water use rates tend to vary a lot when you aggregate it up to an entire MSA or an entire state. And so we were relatively confident using the indoor water use rates. For the outdoor, we did try to calibrate a bit, and really we just used the flume data to kind of get a sense of what the indoor and out, or actually. Actually didn't use the outdoor data as much for the flume data. What we looked at, since we had monthly billing data, we looked at the kind of seasonal water use patterns for each of these utilities and used that to determine how much was indoors and outdoors. And then once we had an estimate of the indoor and outdoor, we used the flume data to then break down that indoor water use into the different fixtures. Once again, based on that kind of assumption that there's not a lot of variation in terms of how indoor water use breaks down across the fixtures between flume users and non-flume users. From what I've seen, the flume data can tend to also skew towards like larger households. So having the per capita metrics instead of the per household metrics for that helped us control for the differences in household size. I
Great.
think,
Okay.
was there a second part of that question? Can't remember.
Well, yeah, Brooke. I think there's a. I think on that first part there was, uh, thoughts on, like, with flume users that they tend to maybe use more water than the typical customer, but then, they may also have a significantly lower leak rate. So,
Oh, right, the leak
yeah.
the leak rate as well. Yeah.
Hmm.
So we did for indoor leaks, we did use the most recent residential end uses of water study for our baseline to determine our baseline of leaks, and I think they estimate a national average of around 14% of indoor water use is from leaks, and then we assume that because the flume users are getting more real-time information about their leaks, are able to intervene earlier and address leaks
Mm.
earlier, though that data reflected our efficiency scenarios.
Thanks, Brooke. We've got a multi-part question here. Did you, and maybe you've already touched upon it a little bit, but did you consider leakage in the residential scenario? For example, if you could speak more to, like, the baseline leakage that you considered. Then, did you incorporate lowering average indoor and outdoor leakage as sort of as an efficiency gain?
Yeah. So yeah, we did consider leakage, although I will qualify that we only looked at kind of what are called low flow leaks, or kind of those consistent ongoing leaks that happen within the home. We didn't look at like major like pipe burst events or anything like that, just because those are, not as easily quantifiable, and the frequency, being able to develop an efficiency scenario to prevent those is it was a little it wasn't quite clear like how to reliably do that. Those tend to be due to extreme events and aging infrastructure that can be unpredictable. So we only kind of looked at the low flow leak portion of kind of total leaks. We didn't, and we assumed, we kind of treated leaks as their own end use, but and kind of lumped in the indoor and outdoor. But of course, how you address those will be different. Sometimes it's as easy as replacing a toilet flapper. Other times it might be replacing an entire irrigation system. But in terms of what the savings potential are, those are kind of all lumped into that leak percentage.
Bruk, a favorite topic of mine, AMI, advanced metering infrastructure. I know WaterSense, we had a few webinars on this topic, and we've got a few documents on this topic. But the question that was posed was, is AMI a consideration on the utility side, and maybe your thoughts on that and how AMI was interplayed in this work.
Yeah, no, that's a great point. And we do talk about AMI in a few different places in the report because it can really help support both identifying kind of customer side leaks, but it can also be used to identify utility. You can kind of use aggregated AMI data for a bunch of for an area within a utility to help isolate utility side leaks and see, for a community, how much water is going in versus how much is being billed, or even how much water is going in versus how much is going to customer meters, and you can try to find that difference. So there are really cool examples of kind of AMI being used for what's called virtual district metering, or understanding kind of how much water use is going into a portion of your water system by aggregating up at a high temporal resolution by aggregating up AMI data from individual users. So we do talk about that a bit in the report, but we didn't. It's not an explicit strategy, but that would be one of the ways to help kind of meet some one of the higher leading edge efficiency scenarios.
Great. Bruk, could you speak more to the data sets that you worked with? Did it include multi-unit residential, or was it mainly single-family homes or such?
So we did have the data set that we had was residential was categorized into residential, commercial, and commercial and total water use for utility. And the researchers that we obtained the data set from had actually merged single family and multifamily into a single residential volume. And so one of the things that I didn't mention originally was that when we were developing our baseline water use estimate, we developed that on the basis of per capita water use. So we normalized it to the individual person, and then we projected that per capita water use rate from the historical data set up to current day, which by the time we were working on the analysis is around 2023 or so. So we projected that per capita water use and then multiplied that by current day population to get what the total water volume is. So in that case, there's really not much of a difference in per capita water use between single family and multifamily. Of course, it changes on a per unit or a per household basis, but in terms of per person, it was reasonable to kind of merge those two together into a single residential category.
As I mentioned, folks, feel free to keep the questions coming. Bruk and I can stay past the hour in case anyone wants to hang back. But yeah, let's keep it going. Bruk, I'm going to jump from the chat to the Q&A. I saw 2 questions trickle in there. This first one is, is there more that you could kind of add, or any commentary you have on CII subsector benchmarking efforts you may have come across? I think that this person at their utility, they were doing some basic non-normalized benchmarking, but they're kind of in the early stages.
Yeah. We in the analysis, we use that water use intensity in terms of gallons per square foot. But there's, a fair amount of evidence that there are better normalizing factors other than square footage that can still lead to that doesn't explain the variation across different CII establishments. Like, for example, if you think about healthcare as a subsector, that can include hospitals, that can include inpatient clinics, that can include like outpatient procedure or like dental offices, those will all have very different rates of water use, and so it's hard to group them all together. Um, for our purposes, we were trying to get kind of just a like as I mentioned, kind of a first attempt at an approach to be able to do this, and then hopefully as we get better data, we can have more refined estimates that can help account. I did a little bit of work in grad school just trying to like control for that variation across the non-residential water demands, and um, what I found was that there are different classification systems out there. Like some people use the NAICS code, which is like an industry classification code. Some people use like land use categories. Um, there's no existing like system that does a great job at capturing all the variation. And so part of it is going to be how you define these subsectors, which is why so many different states and communities have different classification systems. But we have to try to get towards some way to at least have like consistency between them, at least in maybe the number of categories or in how you treat certain like highly specialized industries, which ones you group together. I think that our recommendation is more towards developing consistency across the country, so to help enable that benchmarking. As far as like the water use for different types of benchmarks go, we did do a pretty thorough or exhaustive survey of the existing literature that have looked at CII water use intensity metrics across a different set of drivers, and we summarize those in the report and include them in our references in case you're curious. The benefit of the Energy Star Portfolio Manager kind of classification system is that it is a national system, and so it is something that can be applied across all states. But it won't be the be all end all of classification, and individual utilities might want to look towards, in addition to that system, look towards something that's more specialized, more custom for their service area when they're trying to identify water efficiency savings opportunities.
Brooke, I saw a few questions regarding data centers come in, so why don't we jump into this first one? Any thoughts on how current national data center construction, plus the water use projections associated with them, how that might skew the national savings potentials?
Yeah, so that that's that's a really good question. The construction aspect of these data centers, so like I think is separate from like their kind of ongoing water use when they're operating, and those are both like two very water intensive parts of the process. I think construction in our case, I don't know if we had construction as a dedicated industry. I would have to go back and look at that. But as far as like water use for data centers when they're operating, I mean they end up being pretty like similar to other industrial uses, as well as to things like power generation, in that the overwhelming majority is for cooling, and so one thing that we want to do that's kind of like what we're looking for funding now to look at more deeply is understand the opportunities for industrial and data centers specifically, and kind of trying to get a more granular look beyond kind of what that total volume estimate is based on performance. Kind of what are the savings opportunities from different types of cooling systems, and looking at the trade-off between air cooling, which uses more energy, versus water cooling, which uses more water, as well as opportunities to use other alternative water sources for the cooling in those industrial and data center applications. For example, from like municipal recycled water, as just an example. And that's actually something that we're looking at right now as part of our wastewater reuse assessment that I mentioned.
So what I'm hearing, Brooke, is we're probably going to have you back here for a part 2 webinar, is what I'm hearing.
Oh, hey, yeah, I would.
Yeah.
That would be great. Yeah, it's a fascinating topic, and I'm glad that there's a lot of work, in the water space being done, looking at data centers. But I think it's also important to remember that there's also been like a lot of innovation for cooling, specifically, which ends up being the largest water use for data centers. And so in that sense, while their construction and the rate of construction is new, the types of water use aren't really that different, and so we do have strategies for them.
Brooke, I'm going to jump right back into the Q&A. So a lot of energy goes into pumping water from its source to its end use. It's not just energy from hot water savings. Is there any
Mhm.
quantitative data out there that connects these water results to energy?
Not these results specifically, although there is a ton of research out there looking at the kind of upstream and downstream energy water nexus, kind of beyond the point of use. The research group I was in grad school, the Weber Energy Group, has done a lot of work looking at both the energy use for water distribution and water treatment, as well as the water use for energy. It's something, the energy water nexus. And I know a lot of other researchers, especially out of some of the California universities, have also looked at it, as well as others. So, and I think actually, um, Jonah Shine has actually presented on looking at some of the upstream and downstream energy use impacts of some WaterSense specific technologies, not just within the home, but also outside of the home. So, and that's something we want to take our results and be able to do that type of upstream and downstream, or kind of direct and indirect energy use analysis. Um, to better inform and better make the case for improving water efficiency. That's our next step. That we're looking for funding for that as well. And so hopefully that comes across soon. But yeah, it's definitely of interest. And if you follow up with me, I'm happy to share some resources that could get you started there.
Brooke, one person posed an interesting question. I think this person felt that there was a bit of surprise in seeing the potential shown for Texas. I think maybe folks expected a little bit more water savings potential for that particular state. Um, is there any commentary you want to add with respect to that state? But maybe I'll expand that question broader and ask, when you saw your end results, were there any states or regions that some that you kind of were wondering, like, was the potential more or less than what you expected?
Yeah, I'll take that second part first. That I think the analysis made me. I think part of the surprise for me was looking at opportunities for residential water savings, both indoors and outdoors, more in like the eastern part of the country, which we don't typically associate with um, drought, um, but we do find relatively high rates of, especially for like residential outdoor, we do find relatively high rates of what's called over irrigation, or basically irrigating in excess of what a turf landscape would need. Um, and that could be just due to behavioral patterns. It could be due to, kind of the perception that of abundance of water supply in those areas. But as I mentioned, as some of these areas experience more frequent and more severe kind of summer droughts or seasonal droughts, focusing on residential outdoor water use there could provide dividends in terms of water use savings. For Texas, what I'll mention is that, while a lot of these statewide results kind of mask what's going on in individual communities and towns, and so it's very. I'd have to look at like because we had a few different utility data sets from Texas, and I'd have to look at them individually. But what I do know is that in a lot of cases, individual communities might have larger water use than normal, but that kind of gets masked when you kind of bring it up all the way to the state level, and it really also just depends on which sector and which end use the audience person was talking about. For example, in San Antonio, they have a kind of a cultural and behavioral priority of really embracing deficit irrigation in the summer. At the city perspective, there are going to be individual households that still over irrigate, but um, there's really kind of a long-standing tradition of letting lawns go brown over the summer and not meeting the full irrigation need, because they understand the water supply risks that generates, and so that can get masked when you look at just a state level result, and I'm sure that's happening in other places as well. So we don't say anything about like individual communities, but we kind of just present what's happening when you zoom out to the state. But yes, it's going to be it's going to be the state level results are going to be a mix of over irrigators or like high water users and low water users. And so what happens for the state level potential might just show what's happening when you kind of blend those two together, and it kind of might even out in some cases.
All right. Well, we're at the hour. I want to thank everyone for staying on. If you have to hop off, totally understand. Please join us again in June. But right now, for folks, feel free to stay on. Like we're gonna keep going through all of the questions here in the Q&A. So feel free to stay on. Brooke and I can stay for probably 30 more minutes if need be. We're really excited to keep the discussion going. And so. Um, and I also, again, shout out to our team. We've been putting in resources, WaterSense resources, in response to some of the questions. So let's keep it going. Brooke, the next question that I'm seeing is that reducing water flow can contribute to increased risk of waterborne pathogen development under certain conditions, especially when it leads to stagnation or just longer water residence times. Any
Mhm.
suggestions or commentary on that? I think kind of it's that trade-off of, if we reduce the water flow. So any
Yeah.
thoughts there?
Yeah. There's a concept when I was working on this. There's a concept I was introduced to by someone from IAPMO, the International Association of Plumbing and Mechanical Officials, called the water sanitation nexus. I'd heard of the water energy nexus. I know that there are, can be sanitation concerns, especially when it comes to like cooling towers, for example, and the risk of um, Legionnaire's disease from either unmaintained or stagnant water in cooling towers. But it's a good point that reducing the flow of water going through plumbing can contribute to stagnation and therefore the risk of waterborne pathogens. You know, so there's a couple of different points, and I'll also mention that there's also a concern kind of on the infrastructure side that reducing the volume of water that's entering sewers can make it harder for wastewater treatment plants to treat kind of what more concentrated sewage and wastewater, and so there are a couple of different strategies, that are available. One of the things that we talk about in the report on that topic of kind of behavioral and structural waste is that IAPMO actually did a study a few years ago, really kind of pointing to the fact that a lot of our plumbing systems are like way over designed for how much water they actually need to deliver, and so they end up being oversized because because the design standard that hasn't been updated in decades is based on the assumption of having like every single fixture in a building running at once. And that's how big you need to design your plumbing system for. When in reality, that never happens, except for maybe in places like stadiums or something like that, where everyone leaves and goes to use the bathroom afterwards. But in most buildings, that's not happening. And so so we need to think about better designing our plumbing systems to kind of meet to make sure that we're meeting demand, but not necessarily being so over designed, because that contributes those larger pipes and larger kind of storage capacity in the plumbing can contribute to that stagnation problem. So there's a bit of like a structural kind of design aspect of that question that can be coupled with water efficiency improvements to help mitigate some of that risk. And then on the wastewater treatment side, a lot of our wastewater treatment facilities are relatively old and need to be upgraded and rehabbed, as well as we find kind of new contaminants and pathogens that need to be treated. And so I think, as those facilities need to be redesigned or expanded or rebuilt, there's an opportunity to look towards more flexible treatment processes that aren't so rigid to a single set of like water quality parameters for the wastewater that's entering them, and can be more flexible and how they're designed in order to meet and treat a broader range of flows and concentrations. Of course, that comes with more expense, though. So there's a trade-off there in that flexibility versus cost. But that's something that, as I mentioned, we've seen water use trends. Water use municipal has remained relatively stable as population grows, but per capita water use has gone down, and so they've already been dealing with some places have already been dealing with some of these issues, and all in all, that's not I guess that's not necessarily like a reason to not do water efficiency improvements, but it's something that needs to be accounted for in addition to doing water efficiency improvements.
Brooke, could you provide maybe a little more detail on, I guess, what are the subsets or what's behind? I think this goes back to some of your sector slides. What's behind what makes up food service in your study? Like the subsets or just kind of what's in that grouping?
Yeah, so it came a bit from kind of trying to merge the different data sets that we had used. So, for example, the economic employment data that we used was categorized by the NAICS code, the industry code that's from the North American classification system. Some of the literature data we were using for water use intensity comes from just kind of self-described categories of water use or subsectors of water use. And then you have the EPA portfolio manager categories of water use. And so the subsectors that we identified kind of came from trying to harmonize those three data sets, as well as the commercial building energy consumption survey, which uses an even different classification system, and really just try to capture like the major sectors of water use. So in this case, food service would be anything that involves the preparation and serving of food-related items. So that could be something like a restaurant. It could be a food hall. It wouldn't be like industrial food processing. That was, or like meatpacking plants or anything like that. That would be on the industrial side, but it would be anything where kind of food is served as kind of its main product as part of for the establishment. There's a similar category of like places of assembly. Those are, that's a pretty wide spanning one that can include like things like religious institutions and houses of worship, to stadiums, to concert halls. But they're really areas. The thing that they have in common is that they can often be unoccupied for long portions of time, and then have a large influx of occupants that come for events or things like that.
Hey, well, I'm gonna go ahead and just ask for a last call for questions because I'm seeing we're getting to the bottom of the list, so maybe it's the last call for questions. Brooke, well, the next question that we have was: it seemed like the largest potential savings sector in all of the Western states was categorized as other. If you could speak to this, was this energy, or if it wasn't energy, any perspective or idea of what that fell into that other?
Yeah, so the other category, kind of as I mentioned, was like a catch-all that for establishments that didn't fit in one of the other 9 kind of major subsectors. And so that includes things like really highly specialized uses like laundries and car washes, fitness establishments. So in terms of like where the opportunities are for other, that really just means that none of the major subsectors have the largest opportunity, and it's relatively dispersed across a number of subsectors. And so in those cases, maybe what I should have done was kind of, for the ones that are other, I should have shown like the subsector with the next highest savings opportunity that might have been helpful on a state by state basis. And I'll have to look into that. But really, what that means is that the savings opportunity aren't as concentrated in a single subsector.
Brooke, I think the last question that I'm seeing is how, if you could speak more to how are you quantifying water savings for outdoor water conservation efforts, given changes in annual precipitation and temperature and other parameters?
Yeah, that's a really good question. We didn't look ahead at all, so we didn't really like try to account for future expected changes to climate change, future expected changes to water demands as a result of climate change impacts and other kind of changes to climate variables. But what we did was really develop kind of relationships between water use. Well, so one thing we did was try to control for the effects of historical weather in the historical water use data set. So for each of the utilities, we looked at what since we had a monthly data set, we looked at what the monthly maximum temperature was, the monthly average temperature, and the monthly precipitation for each of those utilities, and then estimated what the water use is in kind of like a quote unquote average weather year based on the past 30 years of weather data for that utility. So, because once we could control for those effects, we could estimate like a counterfactual of what the typical water use is for an average weather year, which we call just like weather normalization. So theoretically, and then since we had to project the water use from the end of the historical period, which was 2017 up to 2023, we just simulated what that water use is current day for the same average weather conditions. So what that means is that each of like the results that we show is based on kind of typical weather years. It doesn't really account for fluctuations, a dry year or a wet year. We could look at those opportunities. That might be something that actually that's a good idea to look at for as a supplement to this work. And then the other thing is that the water savings are driven by kind of meeting some portion of the evaporation needs of a landscape, and those needs change in each efficiency scenario because we're assuming that the evaporation needs are lower and lower than turf in the more ambitious efficiency scenarios. So as evaporation increases, you would need more supplemental water. That's true in order if it's much higher than historical evaporation, for example. But part of the benefit of that approach is that these are like those evaporation needs are determined from region appropriate landscapes, and so theoretically they're based on what's appropriate for each state, for each region. Of course, that doesn't really speak to future impacts as evaporation and precipitation changes, and that's something that we would want to look at in future work.
Bruk, if I could squeeze in maybe one final question, in seeing
Absolutely.
your presentation, it just got me thinking about like, do we need to move collectively to some kind of standardization of CII, water use data, or such? But I also recognize that, folks are going to be moving at a different pace with respect to how they collect and quantify data. So I don't know if you had any thoughts on that.
I think working towards an ideal of a consistent classification system across the country is a great idea. I think the first step would be for utilities and states to just have a classification system, to just acknowledge the variability of CII water use across the different subsectors and try to wrap their heads around how much water use is happening within their service areas or within their state for each of these different subsectors. And a lot of states already have some kind of system, but a lot of areas also just look at CII as a whole. And that doesn't really help much in terms of trying to improve overall CII water efficiency, because the strategies that you would use are going to be so different for a food establishment, a food service establishment where you can install more efficient kitchen pre-rinse spray valves versus a healthcare facility where you might want to look at specialized medical equipment that might use a lot of water. And so having a way to acknowledge that variability and try to collect data that captures that variability, I think is the first step. And you could start with a smaller number of categories, or you can start with, focusing on just the industries or the subsectors that, might be the largest water users or of the most importance in your service area, and then try to expand, iterate little by little. There's some interesting work coming out that looks at bringing in some other data sets, like getting, within a city that might have all of their departments under one organization or under one city structure, getting your water utility to talk to your land use planning people to try to look at land use data and use that to help classify your commercial, your CII water customers. That's going to be harder in rural areas and areas that don't have the resources, of course. And of course, there are also a lot of communities that might have a single large CII customer that really drives a ton of their water use. Referring, like, for example, that data center example, a lot of the new data centers are built in kind of more rural areas where they might end up being the largest commercial water use. And so the approach is going to be different based on what kind of community you're in, but at least being able to understand that variation of CII water use, don't just treat it as a single sector, but really try to dig in and see what's happening at a more granular scale, I think is going to be the first step to at least measuring what's happening.
Well, with that, I want to thank everyone that stuck with us past the hour. Bruk, I suspect that as folks maybe dive into the report, they'll have follow-up questions for you. So I'm glad to have your contact info there. If anyone has any further questions for myself and/or the WaterSense team, feel free to shoot us an email. And again, please join us in June, where I think we're going to be doing more. Our June webinar will dive more into CII and kind of that classification idea. And so with that, everyone, take care. Have a great rest of the day.
Yeah, thank you all.
We're going to turn off the recording.